Hello everyone, welcome to another video on Calculus 1, and I'm still looking at the precise definition of a limit, also known as the epsilon delta definition of a limit. Today I'm focusing on quadratic functions, and I have 3 examples for you. So example number 1 says prove that the limit as x approaches minus 2 of x squared minus x plus 1 is equal to 7. Number 2 says the limit as x approaches 0 of x squared plus x plus 5 is equal to 5. Third one, the limit as x approaches minus 1 of 2x squared minus 3x minus 4 is equal to 1. Now, if you perform a simple substitution of these values into these quadratic expressions, you're going to get these numbers here. But we're supposed to use the precise definition of a limit. So let's get into it. Question 1, as the tradition goes, I have to copy the question. So here are our answers. Number 1, the limit as x approaches minus 2 of x squared minus x plus 1 is equal to 7. Let us state the precise definition of a limit then. It says if the limit, this is our proof now, if the limit as x approaches a of f of x is equal to L, it means for every epsilon greater than 0, there exists a delta greater than 0 such that if the absolute value of x minus a is less than delta but greater than 0, then the absolute value of the function minus the limit should be less than epsilon. That's the precise definition of a limit. Now let us put our limit into the precise definition as follows. Therefore, the limit as x approaches minus 2 there of x squared minus x plus 1 is equal to 7 means for every epsilon greater than 0, there exists a delta greater than 0 such that if the absolute value of x minus 2, absolute value of this is less than delta but greater than 0, then the absolute value of our function x squared minus x plus 1 minus the limit 7 should be less than epsilon. Now we go to the 4 steps given. Step 1, what are we given? That epsilon is greater than 0. Let's look at the choice of delta. Now I want to say it on the outset that whenever you have a quadratic function or any other function other than a linear function, the choice of delta almost all the time will be the minimum of, usually you want the distance between the number and x to be within 1. So it will be the minimum. Our delta, choice of delta, will be the minimum of 1 and some value of delta which we're going to choose. Now, step number 3 is the assumption step. So we assume, what do we assume? We assume that this expression here, which by the way simplifies to 0, is less than the absolute value of x plus 2, which is less than delta. So we assume that that expression there, 0 less than absolute value of x plus 2, is less than delta. We assume that this is true. Remember, the precise definition of a limit says if this is true, then that is true. So if this holds, that should be true. But let's see the value, the choice of delta that we're going to make. Next, we move on to the notice step. Notice what? We notice that this expression here simplifies. Notice that absolute value of x squared minus x plus 1 minus 7 simplifies to the absolute value of x squared minus x minus 6. And if you factorize that expression within the absolute values, you're going to find x minus 3 and then x plus 2, which the absolute value of a product is the product of absolute values. So this will be absolute value of x minus 3 times absolute value of x plus 2. Now if you go back here, absolute value of x plus 2 is less than delta, which means if I substitute delta in this place here, I'm going to get less than absolute value of x minus 3 times delta. My problem is this part here. Now this is where the issue of minimum here comes in. So we assume the distance to be the distance between our a and x to be within 1. Remember, the idea is to find the smallest value, a very small number delta, such that if this is true, that should be true. So now if we look at this part here, we're going to say, all right, let's have our distance, which is absolute value of x over here, x minus 2, our distance between x and minus 2, which is basically the absolute value of x plus 2. Let this one be within 1, less than or equal to 1. By definition of absolute value, you can remove the absolute value signs here. You're going to get x plus 2. This should be less than or equal to 1, but greater than or equal to minus 1. Now, if you look at this expression here, is x minus 3. So we have to get rid of the 2. So you take the positive 2 to that side and that side. In other words, subtract 2 from both sides. From here, there, and there. What you're going to get is minus 1, minus 2, less than or equal to. In the middle, you'll have x, and that will be less than or equal to minus 1. Now, if you look at this part here, is x minus 3. So this is minus 3, less than or equal to x, less than or equal to minus 1. And I need minus 3 in the center. So I'm going to have to say subtract 3 throughout. So minus 3, less than or equal to x minus 3, less than or equal to minus 1, minus 3. And this gives you minus 6, less than or equal to x minus 3, less than or equal to minus 4. Now, if you take absolute value, then the inquiry signs will have to change, because the absolute value of minus 6 is bigger than absolute value of minus 4. So now we're going to say absolute value of minus 6 is 6. This will be greater than or equal to absolute value of x minus 3, and that will be greater than or equal to 4. Absolute value of minus 4 is 4. Now, rewriting this part here, and let me move to the next page. Next page, right. Okay, rewriting this expression, which I'm going to do over here. Right, rewriting this expression here, you're going to get the absolute value of x minus 3 is less than or equal to 6, but greater than or equal to 4. So we're interested in this part here. Absolute value of x minus 3 is less than or equal to 6, which means if I bring 6 here, I'm going to get the expression that is less than or equal to 6 times delta. And at this stage, if I set 6 delta to be equal to epsilon, and solving for delta, I'll get epsilon over 6. Now bring this expression into that place, I'm going to get an expression that's exactly equal to 6 times epsilon over 6. And if you cancel these two out, you're going to get epsilon. This should be the end of our proof. But remember, we have to take this value of delta that we've chosen, bring it over here, which is epsilon over 6 over here. So we're now going to say, we pick the minimum of these two numbers, whichever is smaller. And whichever is smaller between the two of them, if you select it, it will be such that when you place it here and simplify this, manipulate it, it will give you that expression. And let me just give you a clue on how you do that. You utilize this part here. X minus 3 is less than or equal to 6. Maybe at this stage, let's do the checking, because this is the first one on quadratic. expressions. Let's do the checking. So what do you check? You check the condition. Which condition? This condition over here. That's the condition you check. Remember, we say in the precise definition of a limit, we say if this is true, then that should be true. So that's the condition we're checking, the assumption stage. So we're checking 0 is less than the absolute value of x plus 2, and this is less than delta. Now we are saying that our choice of delta is minimum of the two values. Suppose the minimum is epsilon over 6. Suppose that's our minimum. Then we're going to say, and we're focusing on distance, remember, so we can ignore the first part. So we're going to say x plus, absolute value of x plus 2 is less than, remember, epsilon over 6. We're saying, suppose that's our minimum. We have to multiply by 6 throughout. So we're going to have the following expression: 6 times the absolute value of x plus 2, and that's less than epsilon. But 6 is less than. If you check here, if you check in this expression here, there, 6 is actually greater than this part here. So if I take this and I place in the place of 6, that inquiry sign should hold. So the 6 now changes to, take note of this, absolute value of x minus 3 times absolute value of x plus 2. This sign should hold because 6 is greater than, notice this inquiry sign, what it says, 6 is greater than the absolute value of x minus 3. So if I take this and I put in the place of 6, that inquiry sign should hold. Now this simplifies to x minus 3 times x plus 2, absolute value of the whole thing, like so, less than epsilon. Expanding this, we're going to get x squared minus x minus 6 less than epsilon. Now, take note, minus 6 is actually 1 minus 7 over here. You can see it over here, 1 minus 7. So I'm going to replace it by absolute value of x squared minus x plus 1 minus 7. That's less than epsilon. This is exactly what I wanted to achieve. From this condition here, I've been able to produce this. Remember, from that condition there, I've been able to produce that. And that marks the end of the proof. So in the next examples, I'm not going to do the checking. Please do the checking. Right, let's look at example number 2 now. Let's look at example number 2. Number 2 says here, it says the limit as x approaches 0 of x squared plus x plus 5 is equal to 5. So we're supposed to use the precise definition of a limit. We copy the question as the tradition goes. So number 2, it says the limit as x approaches 0 of x squared plus x plus 5, and we're told this is equal to 5. Let us state the precise definition of a limit. It says if the limit, and that's our proof now, if the limit as x approaches a of a function f of x is equal to L, it means for every epsilon greater than 0, there exists a delta greater than 0 such that if the absolute value of x minus a, that one there, x minus a, is less than delta but greater than 0, obviously we're dealing with distance, then the absolute value of our function f of x minus the limit must be less than epsilon. Now let's put this limit into the precise definition as follows. Therefore, the limit as x approaches 0 of x squared plus x plus 5 is equal to 5 means for every epsilon greater than 0, there exists a delta greater than 0 such that if the absolute value of x minus 0 is less than delta but greater than 0, simplifying this, we're getting 0 less than absolute value of x less than delta. If this is true, then the absolute value of the function, which is x squared plus x, x squared plus x, right, x squared plus x plus 5 minus our limit, which is 5. This must be less than epsilon. Now we go to the 4 steps. Given, what are we given? That epsilon is greater than 0. Next we go to the choice of delta. Remember I told you that the choice of delta, as long as the expression is not a linear function, it most likely going to be the limit, the minimum. So delta should be equal to the minimum. Obviously you want the distance to be within 1, so 1, and then we will see what our choice of delta should be. And so we will have to choose the minimum of the two, depending on what the value of epsilon is. So next we're moving to the assumption stage. We assume, or assumption step, we assume that this is true, that 0 is less than the absolute value of x, and that's less than delta. Then we go to the notice stage. What do we notice? We notice that this expression here simplifies, that x squared plus x plus 5 minus 5 simplifies to the absolute value of x. The absolute value of that simplifies to absolute value of x squared plus x, because the 5 minus 5 is 0. And expand, factorizing this expression here, this gives us exactly x open bracket x plus 1, like so, which translates into the absolute value of x times up to absolute value of x plus 1, like so. And we said over here that the absolute value of x is less than delta. So if I put delta here, I'm going to get less than delta times absolute value of x plus 1, like so. This one here is the one that now must go. I need an expression for that. It takes me back to there. So now I'm assuming that my distance between 0 and x should be less than 1 or equal to 1. So I'm going to say absolute value of x should be less than or equal to 1. And what do? I remove the absolute value sign. So I'm going to get x is less than or equal to 1, but greater than or equal to minus 1. And what I have here is x plus 1. So I'm going to have to add 1 throughout. Adding 1 here, I get 0, less than or equal to x plus 1, less than or equal to 2. If I take absolute value of 0, it will be 0, less than or equal to absolute value of x plus 1, I get this. Absolute value of 2, I get 2. And looking at this part here, I have an expression now. If I take 2 and I place here, I'm going to get something that is less than or equal to, over here, I'm going to get less than or equal to delta times 2. Let's go to the next step. In our next step, what are we saying in our next step? We are saying that this is exactly equal to 2 delta. At this stage, like we have done in the previous examples, set 2 delta to be equal to epsilon. Solving for delta, it will be epsilon over 2. And bringing epsilon over 2 into the place of delta here, we're going to get 2 times epsilon over 2, and the 2's cancel. That is going to be epsilon. That should be the end of our proof. With the fact, or considering in mind, or having in mind, bearing in mind that this here, we're not just going to take that as our choice of delta, because we assumed here that the distance should be within 1. So we'll take the minimum of this and 1. So epsilon over 2. Over 2. We're going to take the minimum of epsilon over 2 and 1 there to be our choice of delta. I'm going to say to you, assume that the minimum is epsilon over 2 and do the checking. You must come up with this conclusion here. As you've seen in example 1, I did check. I'm moving on to example number 3. So, example number 3. What does example number 3 say? Here it is. It says that the limit as x approaches minus 1 of 2x squared minus 3x minus 4 is equal to 1. Now, as the tradition goes, I'm going to copy that. So copying it, number 3, the limit as x approaches minus 1 of 2x squared minus 3x minus 4 is equal to 1. Let's state the precise definition of a limit. It says if the limit as x approaches a of f of x is equal to L, it means for every epsilon greater than 0, there must exist a delta greater than 0 such that if the absolute value of x minus a is less than delta but greater than 0, then the absolute value of the function minus the limit is less than epsilon. Let us put our limit into the precise definition as follows. So this is our proof. Obviously, we get, therefore, the limit as x approaches minus 1 of 2x squared minus 3x minus 4 is equal to 1 means for every epsilon greater than 0, there exists a delta greater than 0 such that if the absolute value or distance between x and minus 1, so x minus minus 1, absolute value of this is less than delta but greater than 0, then the absolute value of this function minus the limit must be less than epsilon. 2x squared minus 3x minus 4 minus 1 less than epsilon. Sorry about that. Let's simplify this part here. 0 is less than absolute value of x plus 1, and this is less than delta. We move to the 4 steps. So step number 1, given. What are we given? We're given that epsilon is greater than 0 over here. Next, we move to choice of delta. Remember, I've told you this is quadratic expression. The choice of delta most likely is delta is going to be the minimum. Minimum of what? Of 1 and whatever choice of delta we're going to make. We'll have to choose the minimum of the two. Step number 3, the assumption step. What do we assume? We assume that this is true. We assume that this holds. 0 is less than absolute value of x plus 1, and this is less than delta. Let's go to our last step where we notice that this expression always simplifies. So we have 2x squared minus 3x minus 4 minus 1. It simplifies to the absolute value of that simplifies to absolute value of 2x minus 2x squared minus 3x minus 5. Now, performing quadratic factorization of this, which I want to do on a rough page. Remember, in my algebra video, I've explained to you that if you have 2x squared minus 3x minus 5, you're supposed to factorize this. You take that and that multiply them, get what is known as product. So in this case, it will be minus 10x squared. The middle part or middle term is your sum. So minus 3x, sum of what and product of what? 2 factors of minus 10x squared, whose product is this obviously, and whose sum is that minus 3x. And if you do your checking here, the 2 factors of minus 10, whose sum is minus 3x, minus 10x squared, whose sum is minus 3x, are actually positive 2x and minus 5x. Multiply these out, you get this. Add them up, you get that. So the central part now changes to, we have now 2x squared. Instead of having minus 3x, I'm going to have plus 2x, then minus 5x, minus 5. And then group the terms. The common factor, highest common factor between the HCF of 2x squared and 2x is actually 2x. 2x in there, it's x. 2x in there is 1. The common factor there is going to be minus 5. Minus 5 into minus 5x. X minus 5 into minus 5, 1. this bracket here must always be the same. If it's not the same, you made a mistake here. You must come back to the table and determine the factors again. So we take the common factor x plus 1, and then the other bracket must contain 2x minus 5. So this is what comes in there, x plus 1 and 2x minus 5. So this simplifies to absolute value of x plus, let me check here, x plus 1 times 2x minus 5. Yeah, like so. Now, if you continue further, you're going to get absolute value of x plus 1 times absolute value of 2x minus 5. Now, if you come here, you find that absolute value of x plus 1 is less than delta. So if I put delta here, I'm going to get less than delta times absolute value of 2x minus 5. Again, I have a problem there. I must get rid of this. How do I get rid of this? Well, we come back here. We say the distance should be within 1. That's why we wrote a 1 there. Distance of x minus minus 1. The distance between x and minus 1 over here, which is x plus 1. Absolute value of that should be less than or equal to 1. Remove the absolute value signs, you get x plus 1 less than or equal to 1, but greater than or equal to minus 1. Now here you have 2x minus 5. So I must get rid of, I can actually multiply by 2 throughout first. So multiply by 2 here, I get minus 2. It's less than or equal to, multiply by 2 here, it will be 2x plus 2. Multiply by 2 there, it will be less than 2. 2 times 1 is 2. So at least I have a 2x there, but I need a minus 5. So I must subtract 7 to get minus 5 there. So minus 7 here, it will be minus 2 minus 7 less than or equal to 2x plus 2 minus 7 less than or equal to 2 minus 7. What does it give me here? Minus 9 less than or equal to 2x minus 5, and this is less than or equal to minus 5. 2 minus 7 is minus 5. If I take absolute value, I'll get 9. The inquiry sign now must change to 2x minus 5 greater than or equal to absolute value of minus 5 is obviously 5. Rewriting this, it is 2x minus 5, absolute value of that is less than or equal to 9, but greater than or equal to 5, if you get what I mean. Now, we are interested in this part here. This is the part we're interested in. We're interested in this part here, this part here. We're interested in that part. So it means we can replace absolute value of 2x minus 5 by with a 9. But the question now will change to less than or equal to, because we're saying we have to pick the minimum between whatever value of delta we choose here and our 1 there. So now we move to our next step, which is our last step. So where do we get to now? We're getting to the following. We're saying now this is less than or equal to delta times, remember, we're taking that value 9 there at the end there, that value 9. And so this is exactly equal to 9 delta. Now at this stage we set 9 delta to be equal to epsilon. Solving for delta, we get epsilon over 9. Taking it, bringing it here, you have 9 times epsilon over 9, and the 9's cancel, and your answer is epsilon. That should be the end of the proof, but remember, we have to say that we must choose the minimum between 1 and epsilon over 9. That will be our choice of delta. This is the end of my video for today, where I was focusing on quadratic functions. We had here, just to remind you, that was our first example, our second example, and our third example. So in my next video, like I said, I'm going to be dealing with cubic functions, and after that I'll give 3 examples on cubic functions. Then I'll move on to functions involving the square root, and so perhaps a radical function and a rational function. We're going to look at the epsilon delta definition, applying that definition to those kinds of functions. If you're new to this video, to this channel, please subscribe and give these videos a thumbs up. Share these videos. It will give us the impetus or momentum for us to be able to produce more videos. And by so doing, we are hoping that these videos are making a difference in someone's academic life. All right, see you next time.